let's debrief thinking on the unit circle. The mystery angle here beneath the hole punch is pi over 2. So we're imagining only angles in the unit circle in this interval between pi over 2 and pi. And so we have to decide which of these is always, sometimes, or never true. So the whole trick to these is thinking about what these are describing geometrically about points on the unit circle. So sine x is telling you the y value at a particular angle. And because all the angles are in this interval, I can see that the y values are all positive in that interval. So this is always true. Sine larger than cosine. Well, between pi over 2 and pi, the cosine values, which are the x-coordinates, are always negative, and the y-coordinates are always positive. So again, this is always true. Okay, tangent x greater than 0. So you could think about this as sine x over cosine x greater than 0. So that would happen either if sine and cosine were both positive or sine and cosine were both negative. The problem is, as already discussed, in this interval, sine is positive and cosine is negative. So this is never true. Secant is 1 over cosine. So again, cosine are x values. So in this interval, x values are always negative. So this one is never true. And cosecant is 1 over sine. The y values in this interval are always positive, so 1 divided by a positive number is positive, so this one is always true. So we've got always, always, never, never, always. So how do we think about when sine x equals cosine x? Here's the unit circle. Sine x is a y coordinate, and cosine x is an x coordinate. So what we're really asking is, for what angles are the y-coordinate and the x-coordinate the same? And so for an angle of pi over 4, they're both the same. And down here at 1, 2, 3, 4, 5 pi over 4, they're also both the same. At 3 pi over 4, the magnitude of the x-coordinate and the magnitude of the y-coordinate are the same, but they're opposite signs because this is a negative x-coordinate and that's a positive y-coordinate. Let's solve the equation tan x is negative 1. So tan x is sine over cosine. So let's multiply by cosine, and that gives us sine is opposite cosine. So this is a similar situation to part A. It's just that sine and cosine have the same magnitude but opposite signs. So if one is positive, the other is negative, or vice versa. So again, referring to this image up here, that happens for these other opposite two angles, which are 3 pi over 4 and 7 pi over 4. All right, let's think conceptually about secant of an angle that's very slightly larger than 90 degrees. So very slightly larger than 90 degrees would be here, for example. Secant is 1 over cosine. So let's think about what cosine is at an angle of 90.01. One thing I'm noticing is that because it's in quadrant 2, the cosine is negative. So that means that 1 divided by a negative number is going to be negative, so it's neither of those. The other thing I'm noticing is that the x-coordinate here is very small. It's very close to 0. So 1 divided by a number that is very small ends up being very large. So the answer is a large negative number. There's some ambiguity in the descriptions here. My intention is a number with a large magnitude that is negative. If you said a small negative number, as long as you were sort of thinking the right thing, that's fine. So without a calculator, let's think which is larger, secant or cosecant at 10 degrees. So 10 degrees is sort of here. So let's see, so secant is 1 over cosine. Cosecant is 1 over sine. So let's think about which is larger. At 10 degrees, cosine is clearly much larger than sine. So 1 divided by a large number is going to be smaller than 1 divided by a small number. Therefore, I think cosecant has to be larger. Okay, last one. Cosine opposite x equals cosine x. So this is a special kind of equation called an identity. And the idea is that this equation is true no matter what the value of x is. And the reason this is useful is it helps you simplify situations that you might not know how to think about otherwise. For example, what if I said, tell me what's the cosine of pi over 7 divided by cosine opposite pi over 7? If you didn't know this fact, you might be stuck. You're like, I don't know what cosine pi over 7 is, and cosine opposite pi over 7, you might try and plug it into your calculator, but if you don't have a calculator, what's even happening? But if you know that cosine is the same as cosine opposite x, you'll realize that this denominator is the same as if this were positive, and so you have something divided by itself, which just equals 1. So that was sort of a simple, silly illustration. But in calculus, there are a lot of situations where you'll apply other identities that will let you rewrite a particular expression in a simpler way that will make problems become solvable. So that's why, here, let's write identity here. So that's why we care about things like identities. Now let's think about, what is this identity really saying? There are at least two different ways you could think about this. First, let's think about it as points on the unit circle. So let's imagine an angle x, just any old angle x. And then cosine is telling us the x-coordinate at that angle. So what is cosine opposite x? Cosine opposite x would be if we went through an angle of x, but in the opposite direction. And what I'm noticing here is they have the same x-coordinate. And that's all this is saying. This is saying it doesn't matter which direction the angle goes. It could be a positive angle or a negative angle. If you take the cosine, which gives you the x-coordinates, those are going to be the same. They're going to be equal. So this algebra really just expresses this simple idea that if you imagine these 2 points as the same angle around the unit circle but in opposite directions, they always have the exact same x-coordinate. Another way of thinking about this, let's rewrite it here. So cosine opposite x equals cosine x. Let's think about it in terms of transformations of the graph y equals cosine x. Here is the graph, y equals cosine x. And if you remember what opposite x means horizontal reflection. So let's imagine what happens if you take this graph and you horizontally reflect it. This point becomes this point, and this point becomes that point. This point becomes this point, and this point becomes that point. It's like every point gets mapped onto a corresponding point on the other side of the y-axis. And hopefully it's visually obvious that if you horizontally reflect cosine, you just end up with cosine again. And so that's the other way of reading this equation. The cosine graph equals, or is the same as, the horizontally reflected cosine graph. So you can see the truth of this identity in either of those ways. It might be interesting to think about sine opposite x. What is that equal to? Think about it in terms of sine x, and see if you can come up with a similar identity for sine. Okay, so the goal on the back here is, what if you don't know what the graph of cotangent looks like? Or further down, what if you don't know what the graph of secant looks like? You can figure out what these graphs look like without memorizing them, and you can also do it without laboriously plotting a whole bunch of points. We're going to laboriously plot a whole bunch of points, but it's in service of identifying some helpful patterns that you could use to very rapidly reconstruct the original graph. So let's do it. So I've filled in all these unit circle values for sine and cosine, which you should know. Let's evaluate cotangent. So remember, cotangent is cosine over sine. So what happens when we have 1 divided by 0? That's undefined. And if we were going to graph that over here, at an angle of 0, we have an undefined y value, which we're denoting by this vertical asymptote. We can think in a minute why is an asymptote instead of something else like a removable discontinuity. So root 2 over 2 divided by itself is 1. Actually, other direction. This root 2 over 2 divided by that one is 1. 0 divided by 1 is just 0. This is something divided by itself, but one of them is negative. Here I've got negative 1 divided by 0 is undefined again. This is 1. This is 0. This is negative 1. Okay, so let's plot. So we've got undefined. At pi over 4, we've got a value of 1. At pi over 2, we have 0. At 3 pi over 4, we have negative 1. And then at pi, we have 0 again. So before we continue on, let's think. We've got 2 vertical asymptotes. We've got these 3 points. What does the middle section look like? I think Eliza put it very well when she said, what did she say? She said, whenever sine is close to 0, you have a number divided by a very small number, which becomes very large. So if you think about the unit circle, the sine is very close to 0 around an angle of 0 or around an angle of pi, because that's where the y coordinates are very close to 0. So it's exactly in those two intervals. Here's this like interval around 0 is here, this interval around pi is here. That's exactly where the sine values are very, very small, which means you're dividing by a very, very small number, which means that you're going to have a very, very large y value. So that's what's generating the vertical asymptote here. Over here, when we're a little bit less than pi, the sine value is positive, but remember the cosine value is going to be negative. So when you have a negative number divided by a very small number, that will be a very large negative number. So it sort of looks like this. And then because this function is periodic, the exact same set of things is going to happen in the next interval over and so on. So that's the short version for how you can reconstruct the shape of cotangent for yourself. Is you think, okay, cotangent is cosine over sine. Think, where is sine equal to 0? And that's what gives you your asymptotes. And then think, where is cosine equal to 0? And that gives you your zeros. And then you can think about some of the values on either side, and that's what lets you fill in the middle parts. Here, let's just get the rest of this going. Here we go, like that, and then like that. Lovely. So if you are into writing stuff down, I've written it down here. They're asymptotes because at integer multiples of pi, sine x equals 0. So that's in the denominator, so that makes those values undefined. But when sine x, but at angles near integer multiples of pi, sine x is very small, meaning that cotangent will be very large. And so that's what means they're asymptotes instead of removable discontinuities. And then y zeros at integer multiples of pi plus pi over 2, it's because that's exactly the values where cosine is 0. And 0 divided by something that's not 0 is 0. And so that's where the y values there are 0. Okay, last one. So let's think about the graph of y equals secant x. And instead of making a table of values, let's just use the graph of cosine and think about the values of cosine based on the graph to figure out what secant has to be. So let's look here. At an angle of 0, cosine has a value of 1. 1 divided by 1 is 1. So this blue dot is on the graph of secant because I have 1 divided by the cosine value at that angle. So the same thing is true at 2 pi. The same thing is true at negative 2 pi. Okay, what about pi and negative pi? Cosine takes on the value negative 1. So what does secant do? 1 divided by negative 1 is also negative 1. So these blue points are the same for both cosine and for secant. Okay, let's ask ourselves, where does secant have vertical asymptotes? Well, that must be whenever cosine is 0, and we can see where that happens right here on the graph. So we know that at each of these angles where cosine is 0, the secant graph must have a vertical asymptote. So you can go ahead and fill those in. And what does it look like in between? So let's see. Between negative pi over 2 and pi over 2, let's graph the unit circle real quick. So negative pi over 2 would be here, pi over 2 would be here. So we're talking about this range. So one thing I notice is that cosine between these two angles, cosine's telling me an x-coordinate, and I'm noticing that in this whole half circle, the x-coordinates are always positive. So what that tells me is that the graph between these two asymptotes can't ever go down here, because those would be negative y values. And the x-coordinate, which is what cosine tells you, is only positive y values. So let's think about maybe something that's very close to pi over 2. So if I think about an angle that's very close to pi over 2, cosine is positive. It's a very small positive number. 1 divided by a small number is a very large number. So that must mean that the point is way up here somewhere. The same thing is true if we think about an angle that's not quite at negative pi over 2. So let's imagine over here. It's a negative angle. It's not quite at negative pi over 2. Cosine is positive because the x value is positive there. It's a very small number. 1 divided by a small positive number is a large positive number. And it's symmetric. And so using similar reasoning, you can fill in the rest of these like this. And that is the graph of secant. So think about what you're going to do next time you have to graph secant. What's the fast way of reconstructing this? Step 1 is remember that secant is 1 over cosine, and ask yourself, where do I draw the asymptotes? And then ask yourself, what are the values between the asymptotes? And then reconstruct the middle parts by thinking about approximate values on the unit circle. I hope that that was helpful.